Space, with all its endless wonders and unknowns, continues to fascinate and baffle scientists, astronomers, and thinkers. Among its many enigmas, few phenomena are as awe-inspiring and mysterious as gamma-ray bursts, GRBs. These intense, high-energy explosions of electromagnetic radiation are the most powerful events known in the universe, releasing more energy in mere seconds than our Sun will emit over its entire 10 billion-year lifespan. Despite decades of study, many questions remain about their origins, mechanisms, and implications for the cosmos. Subscribe so you don't miss out on any of these videos. Gamma-ray bursts, first discovered in the late 1960s by military satellites designed to monitor nuclear tests, have since captured the attention of astrophysicists worldwide. These satellites, part of the Vela program, were meant to detect gamma radiation from nuclear explosions on Earth. Instead, they recorded powerful bursts coming from distant regions of space, a discovery that was completely unexpected and sparked a wave of curiosity. This detection marked the beginning of an astronomical journey into the unknown, as the nature of GRBs remained a mystery for many years. The most striking characteristic of gamma-ray bursts is their sheer energy. A typical GRB can last anywhere from a few milliseconds to several minutes, but the energy released in that short period is staggering. It is estimated that the average gamma-ray burst can release as much energy as the Sun would in 10 billion years. This leads to a puzzling question: what kind of cosmic event could possibly generate such an immense burst of energy? The quest to answer this question has led to various theories about their origins, each more compelling and complex than the last. There are two main types of gamma-ray bursts: long-duration bursts, which last more than 2 seconds, and short-duration bursts, which are shorter than 2 seconds. The distinction between these two types has been one of the key developments in understanding GRBs, as it suggests that different types of cosmic events may be responsible for these bursts. Long-duration bursts are now widely believed to be associated with the collapse of massive stars, in a phenomenon known as a supernova. When a star at least 10 times the mass of the Sun runs out of nuclear fuel, its core collapses under the force of gravity, leading to an explosion that can briefly outshine an entire galaxy. In some cases, this supernova can also generate a gamma-ray burst if the conditions are right. Short-duration gamma-ray bursts, on the other hand, are thought to be caused by the merger of two compact objects, such as neutron stars or black holes. When these incredibly dense objects collide, they create a burst of gamma rays that lasts for just a fraction of a second but can be detected billions of light-years away. The discovery of gravitational waves, ripples in space-time caused by such mergers, has further supported this theory. In 2017, for the first time, astronomers detected both a gravitational wave signal and a short gamma-ray burst from the same event, providing strong evidence that neutron star mergers are indeed a source of GRBs. While the general mechanisms behind long and short gamma-ray bursts are becoming clearer, many mysteries remain. One of the biggest questions is how the energy from these cataclysmic events is converted into gamma rays. The leading theory is that these bursts are powered by jets of particles moving close to the speed of light, which are launched from the explosion or merger. As these jets collide with surrounding material, they produce the gamma rays that we observe. However, the exact details of this process are still poorly understood, and more research is needed to fully unravel the mechanisms behind GRBs. Another mystery surrounding gamma-ray bursts is their distribution in space. GRBs are observed from all directions in the sky, which suggests that they are not concentrated in any particular region of the universe. This isotropic distribution indicates that gamma-ray bursts occur in galaxies scattered throughout the cosmos, and that they are not associated with any specific structures or clusters of galaxies. However, their immense distance from Earth, typically billions of light-years, makes it difficult to pinpoint their exact locations and study their environments in detail. In recent years, astronomers have made significant progress in identifying the host galaxies of gamma-ray bursts. By studying the afterglow of a GRB, which is the radiation emitted after the initial burst, they can determine its location with greater accuracy and observe the galaxy in which it occurred. These observations have revealed that long-duration GRBs tend to occur in small, star-forming galaxies, where massive stars are more likely to exist. In contrast, short-duration bursts are found in a wider variety of galaxies, including elliptical galaxies, which are typically older and contain fewer young stars. This difference in host galaxies further supports the idea that long and short GRBs have different origins. The extreme brightness of gamma-ray bursts also makes them valuable tools for studying the distant universe. Because they can be observed from billions of light-years away, GRBs provide a glimpse into the early stages of the cosmos, allowing astronomers to study galaxies and phenomena that existed when the universe was still young. In fact, some of the most distant objects ever observed are gamma-ray bursts, which occurred when the universe was only a fraction of its current age. By studying these ancient bursts, scientists hope to gain insights into the formation and evolution of galaxies, as well as the conditions that prevailed in the early universe. Despite their usefulness as cosmic beacons, gamma-ray bursts also pose a potential threat to life in the universe. A nearby GRB could release enough radiation to strip away the Earth's ozone layer, leaving the planet exposed to harmful ultraviolet radiation from the Sun. Some scientists have even suggested that gamma-ray bursts could be responsible for mass extinction events in Earth's history. However, the likelihood of such an event occurring in the near future is extremely low, as GRBs are rare and typically occur in distant galaxies. One of the most exciting developments in recent years has been the detection of dark, gamma-ray bursts, which are GRBs that do not produce a detectable afterglow in visible light. These dark bursts are thought to occur in regions of space that are obscured by dust, which blocks the visible light from reaching Earth. The discovery of dark GRBs has opened up new avenues of research, as astronomers seek to understand the environments in which these bursts occur and how they differ from traditional, bright, gamma-ray bursts. As technology advances and our ability to observe the cosmos improves, the study of gamma-ray bursts will continue to shed light on some of the most violent and energetic processes in the universe. The next generation of telescopes, such as the James Webb Space Telescope and the Large Synoptic Survey Telescope, will provide even more detailed observations of GRBs and their host galaxies, allowing scientists to probe deeper into the mysteries of these incredible explosions. The study of gamma-ray bursts is not only important for understanding the universe at large, but also for understanding our place within it. These powerful events remind us of the immense forces at play in the cosmos and the fragility of life on Earth. While the probability of a gamma-ray burst affecting our planet is low, the potential consequences are a stark reminder of the dangers that exist beyond our atmosphere. The threat posed by gamma-ray bursts, GRBs, to life on Earth, while small in terms of probability, is something that can't be completely dismissed. To understand the potential impact, we must consider the energy that a nearby burst would unleash. If a GRB occurred within a few thousand light-years of Earth, and its jet happened to be aimed directly at us, the consequences could be devastating. The gamma rays from such an event would interact with the Earth's atmosphere, stripping away the ozone layer and exposing the surface to dangerous levels of ultraviolet, UV, radiation. This could lead to massive biological die-offs, especially affecting life forms that are most vulnerable to UV radiation, such as plankton and other microorganisms at the base of the food chain. Without these foundational organisms, entire ecosystems could collapse, leading to a chain reaction of extinctions. There is some speculation that gamma-ray bursts may have already played a role in Earth's history. Some scientists have proposed that past mass extinction events, such as the Ordovician-Silurian extinction around 450 million years ago, could have been triggered by a nearby GRB. While there is no direct evidence to confirm this theory, the possibility is intriguing and adds another layer of complexity to our understanding of the forces that have shaped life on Earth. Beyond Earth, the potential for gamma-ray bursts to influence life elsewhere in the universe is equally compelling. GRBs are so powerful that they could affect entire galaxies, sterilizing vast regions of space by bombarding planets with deadly radiation. This has led to the hypothesis that gamma-ray bursts could limit the development of life in certain parts of the universe. If a planet is located too close to a region prone to gamma-ray bursts, it might never have the chance to evolve complex life forms, as any budding ecosystems would be repeatedly wiped out by bursts of radiation. This idea, known as the cosmic sterilization hypothesis, suggests that GRBs could be one of the factors that make intelligent life rare in the universe. Interestingly, the distribution of gamma-ray bursts throughout the cosmos may provide clues about where life is most likely to thrive. Some researchers have suggested that life is more likely to develop in parts of the universe that are less active in star formation, as these regions would experience fewer supernovae and gamma-ray bursts. For example, older, elliptical galaxies, which have largely finished their period of active star formation, may be more hospitable to life than young, star-forming galaxies where massive stars frequently explode as supernovae, potentially triggering GRBs. Gamma-ray bursts, as violent and destructive as they may be, are also key players in the cosmic ecosystem. They are thought to play a role in the distribution of heavy elements throughout the universe. When a massive star explodes as a supernova and generates a gamma-ray burst, it produces a vast amount of heavy elements, such as iron, nickel, and gold. These elements are then dispersed into space, where they can eventually become part of new stars, planets, and even life forms. In this way, gamma-ray bursts, despite their destructive power, contribute to the creation of the very materials that make up the universe as we know it. The detection of gamma-ray bursts has also provided important insights into the behavior of black holes and neutron stars. Both types of objects are believed to be closely linked to the production of GRBs, particularly short-duration bursts, which are thought to result from the merger of neutron stars or the collapse of a massive star into a black hole. These cataclysmic events provide scientists with a rare opportunity to study the extreme physics of matter in the most extreme conditions imaginable. By observing GRBs and their afterglows, researchers can gain valuable information about the formation and properties of black holes and neutron stars, shedding light on some of the most enigmatic objects in the universe. In addition to their scientific importance, gamma-ray bursts have become an essential tool for probing the distant universe. Because GRBs are so bright and can be detected from billions of light-years away, they serve as cosmic lighthouses, illuminating the farthest reaches of space. Astronomers can use the light from GRBs to study the properties of galaxies that are too faint to be observed by other means. For example, the light from a GRB passing through the interstellar medium of a distant galaxy can reveal the chemical composition of that galaxy, as well as the presence of gas and dust. This makes gamma-ray bursts a valuable tool for studying the formation and evolution of galaxies in the early universe. One of the most intriguing aspects of gamma-ray bursts is their potential to reveal new physics beyond the standard model of particle physics. GRBs are so powerful that they push the limits of what we currently understand about the behavior of matter and energy in extreme environments. Some scientists have speculated that gamma-ray bursts could be a window into new physical phenomena, such as the behavior of quantum fields at extremely high energies or the properties of dark matter and dark energy. While there is no direct evidence for these ideas yet, the study of GRBs could lead to new discoveries that challenge our current understanding of the universe. In the quest to understand gamma-ray bursts, astronomers have developed increasingly sophisticated techniques for detecting and studying these phenomena. Early observations of GRBs relied on satellite-based instruments, such as the Compton Gamma Ray Observatory, which was launched in 1991 and revolutionized our understanding of gamma-ray bursts. Today, a new generation of space-based telescopes, such as NASA's Swift and Fermi observatories, continues to provide invaluable data on GRBs and their afterglows. These observatories are designed to detect gamma-ray bursts in real time, allowing scientists to quickly follow up with observations from ground-based telescopes. This multi-wavelength approach has been crucial in piecing together the puzzle of GRBs and understanding their origins. Despite the progress that has been made, gamma-ray bursts remain one of the most enigmatic and least understood phenomena in astrophysics. Each new discovery raises more questions than it answers, and the true nature of these incredible explosions is still shrouded in mystery. As our technology continues to improve and new telescopes come online, we can expect to learn even more about GRBs in the coming years. But for now, they remain one of the universe's most tantalizing and awe-inspiring mysteries, reminding us of the vastness and power of the cosmos. One of the most intriguing aspects of GRBs is their role in testing the fundamental principles of physics. Because GRBs produce such high-energy radiation, they provide an opportunity to test the limits of relativity, quantum mechanics, and other physical theories. For example, some researchers have used gamma-ray bursts to search for signs of violations of Einstein's theory of general relativity, which predicts that all photons should travel at the same speed, regardless of their energy. By measuring the arrival times of gamma rays with different energies from a single burst, scientists can test whether higher-energy photons travel faster or slower than lower-energy ones, which could provide evidence for new physics beyond general relativity. The testing of fundamental physics using gamma-ray bursts, GRBs, has led to fascinating, though inconclusive, insights. One area of focus has been the search for discrepancies in the speed of light at high energies. In Einstein's theory of general relativity, the speed of light is constant regardless of the energy of photons. But some alternative theories, such as those involving quantum gravity, suggest that this may not hold true at extremely high energies. By measuring the arrival times of photons from distant GRBs, researchers hope to detect tiny deviations in speed, which could point to new physics beyond the standard model. So far, no such violations have been observed, reinforcing Einstein's theory, but the hunt continues as our detection technology improves. Another area where gamma-ray bursts could help unlock new physics is in the study of dark matter and dark energy. These two mysterious components make up most of the universe's mass-energy content, yet their nature remains elusive. Some scientists speculate that the behavior of gamma-ray bursts in distant galaxies could provide indirect evidence of dark matter. For instance, if the path of a GRB's light is gravitationally influenced by large quantities of unseen mass, believed to be dark matter, this could reveal the distribution of dark matter in those galaxies. Similarly, by analyzing the effects of dark energy on the rate of expansion in the distant universe, gamma-ray bursts could offer clues to understanding this perplexing force. While we are still far from fully understanding how GRBs might be tied to dark matter or dark energy, their usefulness as tools to probe these deep cosmic mysteries is undeniable. Gamma-ray bursts serve as beacons from the distant past, their light traveling across vast expanses of time and space, offering a rare glimpse into the early universe. They act like cosmic time machines, allowing scientists to study conditions that existed billions of years ago, soon after the Big Bang. By analyzing the light from these bursts, astronomers can gather valuable information about the state of the universe at different points in its history. In particular, the study of GRBs has provided insights into the process of cosmic reionization, a crucial epoch in the history of the universe. This era, which occurred several 100 million years after the Big Bang, marks the time when the first stars and galaxies formed, and the universe transitioned from being opaque to transparent. By detecting gamma-ray bursts from the distant universe, astronomers can examine the intergalactic medium, the space between galaxies, during this period and learn about how it became ionized by the first generation of stars and galaxies. This helps piece together the story of how the universe evolved from a hot, dense, and dark state into the complex structure we observe today. Gamma-ray bursts, despite being rare events, have also provided important insights into stellar evolution and the life cycles of stars. For example, long-duration GRBs are believed to be associated with the deaths of massive stars that collapse to form black holes. Studying these bursts helps scientists understand the final stages of stellar evolution, particularly for stars much more massive than our Sun. These stars end their lives in dramatic fashion, and the energy released during their collapse can trigger a gamma-ray burst. Observing such events offers a window into the processes that occur in the cores of dying stars, which are otherwise hidden from direct observation. Not all gamma-ray bursts, however, come from the collapse of massive stars. As mentioned earlier, short-duration GRBs are thought to result from the collision and merger of neutron stars, or the merger of a neutron star with a black hole. These events are equally fascinating, as they involve the most extreme environments known to science, regions of intense gravity and density. When neutron stars merge, they produce a brief but extremely powerful burst of gamma rays, followed by an afterglow that fades over time. These mergers are also prime candidates for the production of gravitational waves, ripples in space-time predicted by Einstein's general relativity and first detected in 2015. The simultaneous detection of gamma-ray bursts and gravitational waves from the same event would be a landmark achievement, offering a new way to study these violent cosmic collisions. In 2017, astronomers made history by detecting both gravitational waves and a gamma-ray burst from the merger of two neutron stars. This event, known as GW170817, confirmed the theoretical connection between short-duration GRBs and neutron star mergers. It also opened up a new era of multimessenger astronomy, where different signals, gravitational waves, gamma rays, and light across the electromagnetic spectrum can be observed from the same cosmic event. This allows scientists to study these phenomena in greater detail and from multiple perspectives, providing a more complete picture of what's happening in the universe. The study of gamma-ray bursts is not limited to their immediate aftermath. GRBs leave behind what is known as an afterglow, which can be observed in X-rays, visible light, and radio waves. This afterglow can last for days, weeks, or even months, providing astronomers with valuable information about the environment surrounding the burst. By analyzing the afterglow, researchers can learn about the properties of the host galaxy, the amount of gas and dust present, and the mechanisms that power the burst. The afterglow also helps scientists pinpoint the exact location of the GRB, allowing them to associate it with a specific galaxy or region of space. One of the biggest challenges in studying gamma-ray bursts is the need for rapid follow-up observations. GRBs are extremely short-lived events, and the gamma rays themselves typically last only a few seconds to a few minutes. This means that astronomers must act quickly to capture the afterglow before it fades away. To address this challenge, scientists have developed sophisticated networks of telescopes that can respond in real time to alerts from space-based gamma-ray detectors. These ground-based telescopes can swing into action within minutes of a GRB detection, allowing for immediate follow-up observations in visible light and other wavelengths. One of the most exciting recent developments in GRB research is the discovery of gamma-ray bursts from the early universe. Some of the most distant GRBs ever detected are from stars that exploded when the universe was less than 1 billion years old. These distant bursts offer a glimpse into the conditions that prevailed in the early universe, at a time when the first stars and galaxies were forming. By studying these ancient GRBs, astronomers can learn about the chemical composition of the early universe, the rate of star formation, and the processes that led to the formation of the first black holes. The detection of such distant GRBs also raises intriguing questions about the nature of the early universe. For example, how could such massive stars have formed so early in the universe's history, when there was relatively little heavy element content to facilitate star formation? What role did gamma-ray bursts play in shaping the evolution of galaxies during this formative period? These are just some of the many unanswered questions that gamma-ray burst research seeks to address. One of the reasons why GRBs are so important in cosmology is that they can be detected at distances where even the brightest galaxies are too faint to observe. This makes them powerful probes of the distant universe, where they can be used to study the properties of galaxies and the intergalactic medium during the universe's early stages. In this sense, gamma-ray bursts are complementary to other tools, such as supernovae and quasars, which are also used to study the early universe but operate in different regions of the electromagnetic spectrum. The future of gamma-ray burst research looks bright, with several new missions planned to further explore these enigmatic phenomena. For example, the upcoming European Space Agency's Athena mission will be equipped with cutting-edge X-ray telescopes designed to observe the afterglows of GRBs in unprecedented detail. Similarly, NASA's upcoming James Webb Space Telescope is expected to contribute to GRB research by observing the light from distant bursts and helping to study the galaxies in which they occur. These new observatories, combined with ground-based telescopes and gravitational wave detectors, promise to revolutionize our understanding of gamma-ray bursts and their role in the universe. The discovery of gamma-ray bursts from distant galaxies also brings attention to the larger-scale structure of the universe. When gamma-ray bursts are mapped across the cosmos, they seem to align with some of the largest known cosmic structures, such as galaxy superclusters and voids. This raises questions about the relationship between GRBs and the distribution of matter on the largest scales. Scientists speculate that GRBs could trace the web of dark matter that underpins the universe's structure, or they could illuminate the role of cosmic voids in shaping the formation and evolution of galaxies. One particularly exciting development in GRB research has been the identification of gamma-ray bursts as a possible tool for measuring the expansion rate of the universe. Traditionally, astronomers have used supernovae, particularly Type I supernovae, to measure cosmic distances and determine the universe's expansion rate, a method known as the cosmic distance ladder. However, some researchers have proposed that gamma-ray bursts could serve as standard candles for cosmology, similar to supernovae. If the intrinsic properties of GRBs can be understood well enough, they could be used to measure distances to galaxies far beyond the reach of supernova observations, potentially offering a new way to study the universe's acceleration and the influence of dark energy. Another area of investigation involves the study of short-hard gamma-ray bursts, SHBs, which are distinct from the longer, softer bursts that are typically associated with the collapse of massive stars. SHBs are thought to arise from the mergers of compact objects, such as neutron stars or black holes. These events are not only fascinating in their own right, but they are also closely linked to the production of gravitational waves. The detection of both gamma-ray bursts and gravitational waves from the same event would provide a wealth of information about the nature of these mergers, as well as the behavior of matter in extreme environments. The detection of gravitational waves in 2015 marked a new era in astronomy, and gamma-ray bursts have played an essential role in this field. The combination of gamma-ray observations and gravitational wave data allows scientists to study these events in ways that would be impossible with either method alone. For example, gamma-ray bursts provide information about the high-energy processes occurring during the merger of neutron stars, while gravitational waves reveal the dynamics of the merger itself. Together, these two types of observations offer a more complete picture of some of the most violent and energetic events in the universe. One notable event that exemplifies this new era of multimessenger astronomy occurred in 2017, when astronomers detected both gravitational waves and a gamma-ray burst from the same source. This event, known as GW170817, was the merger of two neutron stars and marked the first time that both gravitational waves and electromagnetic radiation had been detected from the same cosmic event. The gamma-ray bursts provided crucial information about the behavior of matter during the merger, while the gravitational waves revealed details about the masses and orbits of the neutron stars before their collision. This discovery confirmed long-standing theoretical predictions and opened up new avenues for exploring the universe. The gamma-ray burst associated with GW170817 was relatively weak compared to other GRBs, which led scientists to speculate that we may have observed the burst from an off-axis perspective, meaning that we weren't looking directly down the jet of gamma rays but rather saw it from the side. This has important implications for future observations, as it suggests that many GRBs may go undetected if their jets are not aligned with our line of sight. By combining gamma-ray observations with gravitational waves, astronomers hope to uncover more such events and better understand the population of neutron star mergers in the universe. The role of gamma-ray bursts in shaping the chemical evolution of galaxies is another exciting area of research. When massive stars end their lives in supernova explosions or GRB events, they eject enormous quantities of heavy elements, such as carbon, oxygen, and iron, into the surrounding interstellar medium. These elements are critical for the formation of new stars, planets, and even life itself. By studying the remnants of GRBs and the environments in which they occur, astronomers can gain insights into how these events contribute to the enrichment of galaxies with heavy elements, helping to piece together the broader story of chemical evolution in the universe. The study of gamma-ray bursts also intersects with the search for life beyond Earth. Some scientists have speculated that gamma-ray bursts could play a role in determining the habitability of planets. A nearby GRB could potentially sterilize a planet by blasting it with intense radiation, stripping away its atmosphere, and destroying any life that might exist. If such an event were to occur near a planet in the habitable zone of a star, it could have devastating consequences for life. This has led researchers to investigate whether GRBs might be a factor in the so-called Great Filter, a hypothesized explanation for why we haven't yet detected advanced civilizations elsewhere in the galaxy. While the chances of a gamma-ray burst occurring close enough to Earth to cause significant damage are extremely low, the possibility cannot be entirely ruled out. Some studies have suggested that a GRB could be responsible for past mass extinction events on Earth, though this remains speculative. Regardless, the potential for gamma-ray bursts to impact planetary habitability is an important consideration in the broader search for life in the universe. As technology continues to advance, the study of gamma-ray bursts is poised to enter a new era. The next generation of space telescopes, such as the James Webb Space Telescope and the European Space Agency's Athena mission, will provide unprecedented views of the afterglows and host galaxies of GRBs, allowing scientists to study these events in greater detail than ever before. Meanwhile, ground-based observatories equipped with adaptive optics and other cutting-edge technologies will enable more precise measurements of GRB properties and their environments. The study of gamma-ray bursts is also expected to benefit from advancements in machine learning and artificial intelligence. With the vast amounts of data generated by modern observatories, these tools will be essential for identifying and analyzing GRB signals in real time. By automating the detection and classification of GRBs, researchers hope to accelerate the pace of discovery and uncover new patterns and phenomena that might otherwise go unnoticed. Gamma-ray bursts remain one of the most mysterious and fascinating phenomena in the universe. From their origins in the deaths of massive stars and the mergers of neutron stars to their role in probing the early universe and testing fundamental physics, GRBs offer a wealth of opportunities for scientific exploration. As our observational capabilities continue to improve, we are likely to uncover even more about these enigmatic events and their significance in the broader context of cosmology and astrophysics. Gamma-ray bursts are not just cosmic fireworks. They are powerful tools that help us unlock the secrets of the universe, offering insights into everything from the behavior of black holes to the expansion of the cosmos itself. As we continue to explore the enigmatic world of gamma-ray bursts, GRBs, we must delve deeper into the physical processes that drive these extraordinarily powerful cosmic explosions. At the heart of a gamma-ray burst lies a cataclysmic event that releases a staggering amount of energy in the form of highly energetic radiation. Understanding the mechanisms behind GRBs not only sheds light on these specific phenomena but also reveals broader insights into the nature of extreme astrophysical environments. The leading theory for the most common types of gamma-ray bursts, those lasting more than 2 seconds, referred to as long-duration GRBs, points to the collapse of massive stars. When a star many times the mass of our Sun exhausts its nuclear fuel, its core can no longer support the outer layers against the relentless force of gravity. This results in the star's core collapsing into a black hole or neutron star, and the outer layers are violently ejected in a supernova explosion. During this collapse, intense magnetic fields and high-speed rotation may channel energy into focused jets of material that travel near the speed of light. These jets punch through the outer layers of the collapsing star and, once they escape into space, they produce the gamma-ray emission observed as a GRB. One of the key challenges in studying these jets is understanding how they remain so tightly focused over such vast distances. The jets must be highly collimated to account for the intense bursts of gamma rays detected from distant galaxies, often billions of light-years away. Collimation refers to the process by which the energy in these jets is confined to narrow beams rather than spreading out in all directions. Theoretical models suggest that powerful magnetic fields play a crucial role in this process, guiding and focusing the jets as they blast through the collapsing star. The interaction between these magnetic fields, the rotation of the core, and the relativistic speeds of the jets creates a highly complex and turbulent environment that is still not fully understood. The study of GRBs is also closely linked to research into the production of high-energy particles in the universe. The jets from gamma-ray bursts are thought to accelerate particles to energies far beyond what can be achieved in any laboratory on Earth, potentially even explaining the origin of the most energetic cosmic rays. These cosmic rays, which are charged particles traveling at nearly the speed of light, bombard the Earth from all directions and are among the most energetic particles known in the universe. By studying gamma-ray bursts and their particle acceleration mechanisms, scientists hope to uncover the sources of these cosmic rays and understand how they are able to reach such extreme energies. In addition to particle acceleration, GRBs are also a source of high-energy neutrinos, subatomic particles that are nearly massless and interact only weakly with matter. Neutrinos are produced in the most extreme environments, such as the cores of collapsing stars and the regions near black holes, and they can travel across vast distances without being absorbed or deflected by interstellar material. Detecting neutrinos from GRBs would provide a unique window into the processes occurring deep within these explosive events, revealing details about the inner workings of the collapsing star and the jets that produce the gamma rays. Large-scale neutrino observatories, such as the IceCube Neutrino Observatory located at the South Pole, are searching for these elusive particles, and the detection of neutrinos from a GRB would mark a major milestone in our understanding of these phenomena. Gamma-ray bursts also raise important questions about the nature of black holes. In many GRB scenarios, the core of a massive star collapses into a black hole, which then powers the jets of gamma rays and high-energy particles. However, the exact role that black holes play in GRB production remains a topic of intense debate. Some models suggest that the formation of the black hole itself drives the jets, while others propose that the black hole is not directly responsible for the gamma-ray emission but rather forms as a byproduct of the overall collapse. Understanding the relationship between GRBs and black holes is key to unraveling the full picture of these cosmic events. One way that gamma-ray bursts can provide insights into black hole physics is through the study of the so-called event horizon, the boundary beyond which nothing, not even light, can escape a black hole's gravitational pull. The extreme conditions near the event horizon are expected to produce intense gravitational fields and violent turbulence, which can affect the properties of the jets and the radiation emitted during a GRB. By analyzing the radiation from GRBs, scientists hope to probe the environment near the event horizon and test predictions of general relativity, including the behavior of spacetime in the presence of such strong gravitational forces. Short-duration gamma-ray bursts, SHBs, which last less than 2 seconds, are thought to arise from a different type of catastrophic event, the merger of two compact objects, such as neutron stars or black holes. These mergers produce intense bursts of gamma rays, along with gravitational waves and other forms of high-energy radiation. While short-duration bursts are less common than their long-duration counterparts, they are of particular interest because they are often associated with the production of heavy elements through a process known as R-Process Nucleosynthesis. This process occurs in the extreme conditions of the merger, where neutrons are rapidly captured by atomic nuclei, leading to the creation of elements such as gold, platinum, and uranium. The detection of gamma-ray bursts from these mergers helps to explain how these heavy elements are distributed throughout the universe. The electromagnetic radiation from GRBs also carries information about the interstellar and intergalactic material through which it travels. As gamma rays travel from the source of the burst to Earth, they interact with gas, dust, and magnetic fields along the way. These interactions leave imprints on the radiation, allowing astronomers to study the properties of the material between galaxies and the large-scale structure of the universe. By analyzing the absorption lines and polarization of the radiation from GRBs, researchers can probe the composition, density, and magnetic fields of the interstellar medium in distant galaxies, as well as the gas that exists in the vast spaces between galaxies. One of the more speculative but intriguing possibilities is that gamma-ray bursts could be linked to the presence of dark matter, the mysterious substance that makes up about 85% of the matter in the universe but has so far eluded direct detection. Some theories propose that dark matter could play a role in the formation of the black holes or neutron stars that produce GRBs, or that interactions between dark matter and ordinary matter could influence the behavior of the jets. While these ideas are still highly theoretical, the study of GRBs offers a potential avenue for investigating the nature of dark matter and its role in cosmic phenomena. The most distant gamma-ray bursts also provide valuable information about the early universe. Some GRBs have been detected at redshifts greater than 8, meaning that their light has traveled for over 13 billion years to reach Earth. These bursts occurred when the universe was less than 1 billion years old, during a period known as the Cosmic Dawn. when the first stars and galaxies were forming. By studying GRBs from this era, astronomers can gain insights into the conditions of the early universe, including the formation of the first massive stars and the reionization of the universe, the process by which the first light from stars and galaxies ionized the hydrogen gas that filled the cosmos. As observational techniques improve, scientists are hopeful that even more distant gamma-ray bursts will be detected, potentially providing glimpses of the universe's earliest epochs. Future space missions, such as NASA's upcoming gamma-ray burst mission, GRAIL, and the European Space Agency's Theseus project, are designed to search for GRBs from the first billion years of cosmic history, offering new opportunities to study the birth and evolution of the universe's first structures. Gamma-ray bursts from the early universe are particularly valuable for their potential to reveal information about the very first stars, also known as population 3 stars. These stars are thought to have been incredibly massive, perhaps hundreds of times the mass of our Sun, and they played a critical role in shaping the universe in its infancy. Because population 3 stars would have been composed almost entirely of hydrogen and helium, the only elements produced in significant amounts during the Big Bang, they are expected to have behaved quite differently from the stars we see today. The collapse and death of these stars would likely have produced intense gamma-ray bursts, providing a glimpse into the processes that occurred during the universe's earliest epochs of star formation. However, detecting such ancient bursts is a significant challenge due to the vast distances involved and the dimming of light over cosmic time. When gamma-ray bursts occur at such extreme distances, they carry with them not only information about the stars that produced them but also about the intergalactic medium, the tenuous gas that fills the space between galaxies. As the gamma rays from these bursts pass through the intergalactic medium, they interact with the gas and leave behind subtle signatures that can be detected by astronomers. By analyzing these signatures, scientists can learn about the composition and structure of the early universe, including how matter was distributed and how the first galaxies began to form. This makes gamma-ray bursts a powerful tool for cosmology, allowing researchers to probe the universe at a time when it was still in its infancy. Another fascinating aspect of gamma-ray bursts is the role they may have played in shaping the evolution of galaxies. The energy released in a gamma-ray burst is so immense that it can have a profound effect on its surroundings, potentially triggering or disrupting star formation in nearby regions of a galaxy. When a GRB occurs, the gamma rays can ionize large amounts of gas, preventing it from collapsing to form new stars. In this way, GRBs could influence the evolution of galaxies by suppressing or altering the star formation process. Alternatively, the shockwaves produced by a GRB may compress surrounding gas, triggering new waves of star formation. Understanding the interplay between gamma-ray bursts and their host galaxies is an active area of research, with the potential to reveal new insights into the complex processes that govern galaxy evolution. Gamma-ray bursts also provide a unique opportunity to study relativistic jets, which are beams of particles that travel close to the speed of light. These jets are not only produced by GRBs but are also found in other high-energy astrophysical phenomena, such as active galactic nuclei, AGN, and pulsar wind nebulae. However, the jets produced by gamma-ray bursts are among the most extreme known, and they offer a natural laboratory for studying the physics of relativistic outflows. One of the key questions researchers hope to answer is how these jets are launched and what mechanisms allow them to travel at such high velocities without dispersing. The extreme conditions in a GRB jet provide a testing ground for theories of particle acceleration, magnetic field generation, and relativistic fluid dynamics. As scientists study the properties of gamma-ray bursts in greater detail, they have discovered that not all GRBs are created equal. In fact, there is a wide range of variability in the characteristics of these bursts, from their duration and energy output to the frequency and intensity of their radiation. Some gamma-ray bursts exhibit rapid variability on timescales of milliseconds, while others have more gradual light curves. This diversity suggests that there may be multiple mechanisms capable of producing gamma-ray bursts, or that different types of progenitor systems, such as stars with different masses or rotation rates, lead to different kinds of bursts. Understanding this variability is crucial for developing a unified model of gamma-ray bursts and for interpreting the wealth of data that comes from gamma-ray observatories. One intriguing discovery related to this variability is the existence of ultra-long gamma-ray bursts, which last significantly longer than typical GRBs, sometimes for several hours. The origin of these ultra-long bursts is still a mystery, but one possibility is that they are produced by the collapse of an unusually large star or by the tidal disruption of a star by a supermassive black hole. In the latter scenario, a star wandering too close to a black hole would be torn apart by the intense gravitational forces, with the debris spiraling into the black hole and producing a gamma-ray burst in the process. These ultra-long bursts may represent a distinct class of gamma-ray events, with different physical processes driving their extended duration. Another class of gamma-ray bursts that has generated considerable interest is the so-called dark GRBs. These bursts are detected in gamma rays but are either very faint or entirely absent in optical wavelengths. Dark GRBs are thought to occur when the gamma-ray burst is enshrouded by thick clouds of gas and dust, which block the visible light from reaching Earth. This obscuration makes it difficult to study the host galaxies of dark GRBs, as the optical afterglows, which are usually used to pinpoint the location of the burst, are not visible. However, the infrared and radio emissions from these bursts can sometimes be detected, providing alternative methods for studying dark GRBs and their environments. One of the most significant advancements in the study of gamma-ray bursts has been the ability to detect their afterglows across a wide range of wavelengths, from X-rays to radio waves. These afterglows provide a wealth of information about the environment surrounding the burst and the interaction of the relativistic jets with the surrounding material. As the jets plow through the interstellar medium, they produce shockwaves that heat the gas and cause it to emit radiation at various wavelengths. By observing the afterglows of GRBs over time, scientists can trace the evolution of the explosion and learn about the density and composition of the materials surrounding the burst. The ability to detect GRB afterglows has also enabled the study of orphan afterglows, which are thought to be the remnants of gamma-ray bursts that were not detected in gamma rays either because the burst was too faint or because the jet was not pointed in our direction. Since gamma-ray bursts are highly collimated, only a small fraction of bursts are directed toward Earth and thus detected as GRBs. However, the afterglows of these off-axis bursts can still be visible in other wavelengths, providing indirect evidence of the gamma-ray burst. Orphan afterglows are an important piece of the puzzle in understanding the true rate of gamma-ray bursts in the universe, as they may represent a significant population of undetected bursts. Another important discovery in the field of gamma-ray bursts is the association of short-duration GRBs with gravitational wave events. The merger of two neutron stars, or a neutron star and a black hole, can produce both a gamma-ray burst and ripples in space-time known as gravitational waves. The first confirmed detection of both a gamma-ray burst and gravitational waves from the same event occurred in 2017, when the LIGO and Virgo observatories detected a gravitational wave signal from the merger of two neutron stars, followed shortly thereafter by the detection of a gamma-ray burst from the same region of the sky. This landmark observation provided a direct link between gamma-ray bursts and compact object mergers, confirming the theoretical models that had predicted this connection. The detection of gravitational waves from gamma-ray burst events has opened up a new era of multimessenger astronomy, in which different forms of radiation, gamma rays, gravitational waves, neutrinos, and electromagnetic radiation at all wavelengths, are used together to study the same event. This multi-messenger approach provides a more complete picture of the physical processes occurring in these extreme environments, allowing scientists to probe deeper into the nature of GRBs and their progenitors. The combination of gravitational waves and gamma rays, in particular, provides a powerful tool for studying the properties of neutron stars and black holes, including their masses, spins, and internal structure. As the field of gamma-ray burst research continues to evolve, new missions and observatories are being developed to push the boundaries of what we can observe. Space-based telescopes such as the Fermi Gamma-Ray Space Telescope, the Neil Gehrels Swift Observatory, and the upcoming Theseus mission are designed to detect and study gamma-ray bursts in unprecedented detail. These observatories are equipped with a variety of instruments that can observe gamma-ray bursts across multiple wavelengths, from gamma rays to X-rays, ultraviolet, and even optical and infrared light. By combining observations from these different wavelengths, astronomers can gain a more comprehensive understanding of the physical processes driving GRBs and their afterglows. In addition to space-based telescopes, ground-based observatories are also playing a critical role in advancing our understanding of gamma-ray bursts. One such observatory is the Cherenkov Telescope Array, CTA, which is designed to detect the highest energy gamma rays, in the TeV range, from astronomical sources such as gamma-ray bursts. When these high-energy gamma rays enter Earth's atmosphere, they produce a cascade of particles that emit faint flashes of light known as Cherenkov radiation. By capturing these flashes, the CTA can reconstruct the properties of the original gamma rays, providing a window into the most energetic and extreme astrophysical phenomena. Observing gamma-ray bursts in the TeV range is especially exciting because it can reveal new insights into the particle acceleration mechanisms and magnetic fields at work in GRBs. Beyond their astrophysical significance, gamma-ray bursts have also become important in the context of fundamental physics. For example, they offer a means to test Einstein's theory of general relativity in the regime of strong gravitational fields and high velocities. One of the key predictions of general relativity is the constancy of the speed of light, regardless of the energy of the photons. By measuring the arrival times of photons of different energies from gamma-ray bursts, scientists can test whether this principle holds true across vast cosmic distances. Any deviation from the expected arrival times could indicate a breakdown of general relativity and hint at new physics, such as quantum gravity effects. In fact, some theories of quantum gravity, such as loop quantum gravity and string theory, predict that the speed of light might vary slightly depending on the energy of the photons, due to the quantum structure of spacetime at extremely small scales. Gamma-ray bursts, with their extremely high-energy photons traveling across billions of light-years, provide a natural laboratory for testing these theories. Although no definitive deviations from general relativity have been observed so far, gamma-ray bursts remain one of the best tools for probing the nature of spacetime and the limits of our current understanding of physics. Gamma-ray bursts have also been used to place constraints on the properties of dark matter, one of the most mysterious components of the universe. Dark matter does not interact with light or other forms of electromagnetic radiation, making it invisible to telescopes, but its gravitational effects can be observed on galaxies and large-scale cosmic structures. Some models of dark matter suggest that it could occasionally interact with ordinary matter or produce high-energy particles, such as gamma rays. By studying the distribution of gamma-ray bursts and their interactions with the cosmic web, the large-scale structure of matter in the universe, scientists can search for indirect evidence of dark matter and test competing models of its nature. In the context of cosmology, gamma-ray bursts are also valuable as standard candles for measuring the expansion of the universe. Although supernovae have traditionally been used for this purpose, gamma-ray bursts offer an alternative method that can probe much greater distances. Because the energy output of gamma-ray bursts is so immense, they can be observed at distances far beyond the reach of supernovae, potentially providing a way to measure the expansion rate of the universe at earlier epochs. By comparing the observed brightness of gamma-ray bursts at different redshifts with theoretical models of cosmic expansion, researchers can refine their estimates of key cosmological parameters, such as the Hubble constant, the density of dark energy, and the overall geometry of the universe. This brings us to another critical mystery that gamma-ray bursts may help to solve: the true nature of dark energy. Dark energy is the mysterious force that is driving the accelerated expansion of the universe, and its properties remain poorly understood. Gamma-ray bursts, because they can be detected across such vast distances, offer a unique way to study how the expansion rate of the universe has changed over time. By mapping out the distribution of gamma-ray bursts over cosmic history, scientists can trace the influence of dark energy on the growth of cosmic structures and test competing theories about its origin. This makes gamma-ray bursts not just astrophysical phenomena but also crucial probes of the fundamental forces shaping the universe. Interestingly, gamma-ray bursts may also play a role in the search for extraterrestrial life. While the extreme radiation from a nearby gamma-ray burst would be devastating for life on Earth, gamma-ray bursts could have different implications for life elsewhere in the universe. Some researchers have speculated that the high-energy radiation from gamma-ray bursts could catalyze chemical reactions in planetary atmospheres, potentially creating the complex organic molecules necessary for life. In this way, gamma-ray bursts could have both destructive and creative roles in the universe, depending on the distance at which they occur relative to planets with the potential for life. The possibility that gamma-ray bursts could influence the development of life also raises interesting questions about the cosmic habitability zone, the region of a galaxy where conditions are most favorable for life to emerge. In addition to factors like the availability of heavy elements and the presence of stable planetary systems, the frequency of gamma-ray bursts could be a key factor in determining whether life is likely to arise in a given region of a galaxy. For example, regions closer to the galactic core, where stars are more densely packed, may be more prone to gamma-ray bursts, making them less hospitable for life. Conversely, regions in the outer reaches of galaxies, where stars are more widely spaced, may be relatively safe from the destructive effects of GRBs, increasing the likelihood of life. The connection between gamma-ray bursts and the potential for life also ties into broader questions about the anthropic principle, which suggests that certain aspects of the universe appear to be fine-tuned for the existence of life because we live in a universe where life is possible. Some researchers have proposed that the frequency and distribution of gamma-ray bursts may be one of the factors that determine the habitability of the universe. If gamma-ray bursts were more frequent or more powerful, they might have sterilized large regions of the universe, making the emergence of life much less likely. In this sense, the existence of life in the universe may depend, in part, on the characteristics of gamma-ray bursts and the conditions that allow life to persist in spite of them. The study of gamma-ray bursts also has practical implications for space exploration. As humanity looks to the stars and contemplates the possibility of interstellar travel, understanding the hazards posed by gamma-ray bursts becomes increasingly important. A nearby gamma-ray burst could pose a serious threat to astronauts and spacecraft, particularly if it occurred without warning. Developing early warning systems that can detect the initial stages of a gamma-ray burst could be crucial for protecting future space missions. Additionally, studying the effects of gamma-ray bursts on the space environment, such as their impact on radiation levels and the behavior of charged particles, could inform the design of spacecraft and habitats that can withstand the harsh conditions of space. As we continue to push the boundaries of gamma-ray burst research, new questions and challenges will undoubtedly arise. One of the most exciting prospects for the future is the possibility of detecting gamma-ray bursts from even more distant parts of the universe, potentially revealing information about the very first stars and the earliest epochs of cosmic history. Upcoming missions and observatories, such as the James Webb Space Telescope and the Square Kilometre Array, will be crucial for achieving this goal. These next-generation observatories will have the sensitivity and resolution needed to detect faint gamma-ray bursts from the edge of the observable universe, providing new insights into the processes that shape the cosmos in its infancy. In addition to observational advances, theoretical models of gamma-ray bursts are also becoming increasingly sophisticated. Advances in computer simulations and numerical modeling are allowing scientists to explore the complex physics of gamma-ray bursts in greater detail than ever before. These models are crucial for understanding the mechanisms that drive the formation of gamma-ray bursts, the structure of their jets, and the interactions between the burst and its surrounding environment. By comparing the predictions of these models with observational data, researchers can refine their understanding of the underlying physics and test competing theories of gamma-ray bursts. As the field of gamma-ray burst research continues to evolve, it is clear that these enigmatic events will remain a central focus of astrophysical inquiry for years to come. Gamma-ray bursts offer a unique window into some of the most extreme and powerful processes in the universe, from the birth and death of stars to the behavior of matter under extreme conditions. They also provide invaluable clues about the history and structure of the universe, offering a means to probe cosmic distances, test the laws of physics, and explore the nature of dark matter and dark energy. In this sense, gamma-ray bursts are not just cosmic explosions but keys to unlocking some of the deepest mysteries of the universe. Gamma-ray bursts also have the potential to influence a wide array of fields beyond astrophysics, extending their significance into technology and even philosophical debates about the nature of the universe. The high-energy radiation produced by these cosmic explosions, for example, offers insights into the behavior of matter under extreme conditions, knowledge that can be applied to more practical technological fields. Understanding how gamma rays interact with matter at such high energies has already influenced advancements in medical imaging technologies, such as PET scans, positron emission tomography, which rely on the detection of gamma radiation to visualize processes occurring inside the body. By studying gamma rays in the cosmos, scientists refine the models that help improve imaging precision in medicine and other areas. Moreover, the computational tools used to model gamma-ray bursts are not limited to astronomy. The extreme complexity of simulating these events, involving fluid dynamics, particle physics, and radiation transfer, has led to the development of sophisticated algorithms and simulation techniques. These innovations have applications in fields ranging from climate modeling to the simulation of plasma in fusion reactors, where understanding the behavior of high-energy particles is critical. In this way, the study of gamma-ray bursts drives technological innovation, providing new tools that can be applied to a variety of scientific disciplines. Moving from technology to philosophy, gamma-ray bursts also open up important discussions about the nature of the universe and our place within it. These violent, high-energy events force us to confront the immense power and scale of the cosmos, highlighting how fragile life on Earth truly is. The fact that a single gamma-ray burst could potentially sterilize an entire planet underscores the randomness and unpredictability of cosmic events. Philosophers have long debated the implications of this cosmic unpredictability, particularly when it comes to the anthropic principle, which posits that the universe's fundamental constants appear fine-tuned for life because only in such a universe could observers, like us, exist to notice them. The discovery and study of gamma-ray bursts lend a new layer to these philosophical discussions. If gamma-ray bursts were more frequent or distributed differently, it is possible that life as we know it could never have evolved, at least not in the forms we see today. This leads to intriguing questions about the role of chance in the development of life and the possibility of intelligent civilizations elsewhere in the universe. Are we fortunate to live in a relatively gamma-ray burst-free region of the galaxy? If gamma-ray bursts had been more frequent in the early universe, would civilizations elsewhere have developed at all, or would the violence of these events have prevented the rise of complex life? Furthermore, gamma-ray bursts provoke questions about determinism and chaos in the universe. On the one hand, the events leading up to a gamma-ray burst are governed by the deterministic laws of physics, such as the collapse of a massive star or the merging of neutron stars. On the other hand, the precise location, timing, and energy of each gamma-ray burst seem to be unpredictable and chaotic. This raises deeper questions about the balance between order and chaos in the universe, and the extent to which we can predict or control such cataclysmic events. Gamma-ray bursts also intersect with questions about the future of life in the universe, particularly in the context of cosmic evolution and the ultimate fate of the universe. Some researchers have speculated that gamma-ray bursts could play a role in shaping the long-term evolution of galaxies by regulating star formation. If a gamma-ray burst occurs in a dense star-forming region, the radiation from the burst could halt star formation by heating up the surrounding gas, preventing it from collapsing to form new stars. Over time, this feedback mechanism could influence the structure and composition of galaxies, determining which regions remain active in star formation and which ones become dead zones, devoid of new stars. At the same time, gamma-ray bursts may offer clues about the fate of the universe itself. If gamma-ray bursts become less frequent over time, this could reflect changes in the rate of star formation as the universe ages. As the universe continues to expand and cool, fewer massive stars will be formed, and the events that lead to gamma-ray bursts will become rarer. Studying the history of gamma-ray bursts and their distribution across cosmic time can help us understand how the universe is evolving and what the distant future holds. In this sense, gamma-ray bursts are not just catastrophic events, they are markers of cosmic history, offering a glimpse into the life cycle of galaxies and the ultimate destiny of the cosmos. The role of gamma-ray bursts in the history of the universe also invites speculation about their potential connection to other mysterious astrophysical phenomena, such as fast radio bursts, FRBs. FRBs are brief but powerful bursts of radio waves, whose origins remain largely unexplained. Some researchers have suggested that there may be a link between gamma-ray bursts and fast radio bursts, with the two phenomena representing different stages or manifestations of the same underlying process. For example, a fast radio burst could occur as a precursor to or a byproduct of a gamma-ray burst, providing a clue about the physical processes that give rise to these energetic events. Alternatively, gamma-ray bursts and fast radio bursts could be related through the environments in which they occur. Both phenomena are associated with extreme astrophysical conditions, such as the collapse of massive stars or the merger of compact objects like neutron stars. Studying the connections between these events could help scientists identify the common physical processes that drive them, offering new insights into the most extreme conditions in the universe. As the search for the origins of fast radio bursts and other cosmic phenomena continues, gamma-ray bursts remain at the forefront of research, offering a window into the most violent and energetic events in the universe. They serve as natural laboratories for studying high-energy astrophysics, providing crucial data that helps refine our understanding of black holes, neutron stars, and the behavior of matter under extreme conditions. As we continue to uncover the mysteries of gamma-ray bursts, it is clear that these events will remain a cornerstone of astrophysical research for years to come, with the potential to revolutionize our understanding of the universe in ways we cannot yet imagine. In the grand scheme of cosmic events, gamma-ray bursts remind us of both the beauty and danger of the universe. They are among the most powerful and awe-inspiring phenomena we have ever observed, and yet they also pose a profound existential threat. Their study pushes the boundaries of human knowledge, forcing us to confront the limits of our understanding while opening new avenues of inquiry into the fundamental nature of the universe. Whether they are helping us unlock the secrets of star formation, test the laws of physics, or explore the potential for life in the universe, gamma-ray bursts are a key to solving some of the greatest mysteries of the cosmos. Gamma-ray bursts continue to fascinate scientists because of their sheer intensity and the fundamental questions they raise about the workings of the universe. While they are among the most powerful events ever detected, there is still much to uncover about their underlying mechanisms, origins, and potential impact on the evolution of galaxies, planetary systems, and life itself. Given their importance, researchers have developed increasingly sophisticated tools to study them, combining data from different wavelengths of the electromagnetic spectrum, ranging from radio waves to gamma rays, to build a more complete picture of these cosmic explosions. One of the most promising areas of research is the study of the environments in which gamma-ray bursts occur. Gamma-ray bursts can originate from different types of astrophysical events, such as the collapse of massive stars or the merger of neutron stars, and each of these environments offers clues about the properties of the burst itself. For example, gamma-ray bursts from supernovae tend to be accompanied by a distinct signature in the optical and radio wavelengths, as the explosion generates shock waves that interact with the surrounding interstellar medium. By studying the aftermath of these explosions, astronomers can learn more about the physical processes involved in the burst and the characteristics of the host galaxy. Observations of gamma-ray bursts have also led to important discoveries about the early universe. Because gamma-ray bursts are so bright, they can be seen across vast distances, making them excellent probes of the distant universe. Some gamma-ray bursts have been observed from billions of light-years away, meaning that the light from these events left its source when the universe was still very young. By analyzing the light from these ancient bursts, scientists can gather valuable information about the conditions in the early universe, including the formation of the first stars and galaxies. This ability to observe gamma-ray bursts across such large distances has also raised intriguing questions about their role in cosmic evolution. Some researchers have suggested that gamma-ray bursts may have played a key role in shaping the structure of the universe by influencing star formation and the distribution of matter. For example, a gamma-ray burst occurring in a dense region of gas could disrupt the process of star formation by ionizing the gas and preventing it from collapsing to form new stars. Over time, this process could affect the structure of galaxies, creating regions with different rates of star formation and altering the overall distribution of matter in the universe. There is also growing interest in the connection between gamma-ray bursts and the formation of black holes. Many gamma-ray bursts are thought to occur when a massive star collapses at the end of its life, creating a black hole in the process. The energy released during this collapse powers the gamma-ray burst, making it one of the brightest events in the universe. Studying these bursts can provide valuable insights into the formation and growth of black holes, which are thought to play a crucial role in the evolution of galaxies. In particular, gamma-ray bursts offer a unique opportunity to study the behavior of matter and energy near the event horizon of a black hole, where the effects of gravity are extreme. By analyzing the radiation produced during a gamma-ray burst, astronomers can learn more about the physical conditions near a black hole, including the dynamics of the accretion disk and the behavior of magnetic fields. This information is essential for understanding how black holes grow and influence their surroundings, particularly in the early universe when supermassive black holes were forming at the centers of galaxies. In addition to their astrophysical significance, gamma-ray bursts also have implications for the search for extraterrestrial life. One of the key challenges in the search for life beyond Earth is understanding the environmental conditions that are necessary for life to exist and thrive. While we have a fairly good understanding of the conditions required for life on Earth, the possibility that gamma-ray bursts could sterilize entire planets raises important questions about the potential habitability of planets elsewhere in the universe. If gamma-ray bursts are common in certain regions of the galaxy, it could limit the number of planets that are capable of supporting life. Planets that are too close to the source of a gamma-ray burst could be exposed to lethal doses of radiation, wiping out any existing life forms and preventing new life from developing. On the other hand, planets located in more stable regions of the galaxy, far from the potential sources of gamma-ray bursts, may be more likely to harbor life. Understanding the distribution and frequency of gamma-ray bursts is therefore critical for identifying potentially habitable planets and assessing the likelihood of life elsewhere in the universe. Furthermore, the potential threat posed by gamma-ray bursts has led to discussions about the resilience of life and the possibility that advanced civilizations could develop ways to protect themselves from cosmic disasters. Some researchers have speculated that highly advanced civilizations might have the capability to detect and predict gamma-ray bursts, allowing them to take protective measures, such as building radiation shields or relocating to safer regions of space. The development of such technologies could be a crucial factor in the long-term survival of intelligent civilizations, particularly if gamma-ray bursts pose a significant threat over cosmic timescales. The search for extraterrestrial life and the potential impact of gamma-ray bursts also tie into broader questions about the rarity of intelligent civilizations in the universe. One of the enduring mysteries in the search for extraterrestrial life is the Fermi paradox, which asks why we have not yet detected any signs of advanced civilizations, despite the vast number of potentially habitable planets in the galaxy. Some researchers have suggested that gamma-ray bursts could be one of the factors that explain the apparent absence of intelligent civilizations. If gamma-ray bursts are capable of periodically sterilizing entire regions of the galaxy, it could limit the number of civilizations that are able to develop and survive over long periods of time. This idea, known as the cosmic catastrophe hypothesis, suggests that gamma-ray bursts and other cosmic disasters could act as a kind of filter, preventing most civilizations from reaching a level of technological advancement where they can survive such events. If this hypothesis is correct, it could mean that the galaxy is filled with the remnants of civilizations that were wiped out by gamma-ray bursts or other cosmic catastrophes before they could establish contact with other intelligent beings. At the same time, the study of gamma-ray bursts offers hope that advanced civilizations could find ways to overcome these challenges. By understanding the physics of gamma-ray bursts and developing technologies to protect themselves from cosmic radiation, intelligent civilizations could increase their chances of surviving in a universe that is often hostile to life. This idea has implications not only for the search for extraterrestrial life but also for the future of humanity. As we continue to explore the cosmos, we may one day face the same challenges that gamma-ray bursts pose to other civilizations. Understanding these threats and developing strategies to mitigate them could be essential for the long-term survival of life in the universe. Gamma-ray bursts represent one of the most powerful and enigmatic phenomena in the universe, offering a wealth of information about the extreme conditions of matter and energy, the life cycles of stars, and the evolution of galaxies. Their study has broad implications for fields ranging from astrophysics and cosmology to philosophy and the search for extraterrestrial life. As we continue to unravel the mysteries of these cosmic explosions, we are likely to gain new insights into the fundamental workings of the universe and our place within it. Gamma-ray bursts, while offering invaluable insight into the nature of the universe, remain an enduring enigma that has sparked continuous research and theoretical exploration. As astronomers and astrophysicists push the limits of observational technology and data analysis, they unravel not only the origins of these high-energy events but also their profound effects on the cosmic environment. The study of gamma-ray bursts stretches across various areas of astrophysics, including black holes, supernovae, neutron stars, and even the very fabric of space-time itself. One fascinating aspect of gamma-ray bursts is the afterglow phenomenon. After the initial burst of gamma rays, these events often leave behind an afterglow that can be detected across a wide range of wavelengths, from X-rays to optical and radio frequencies. This afterglow provides crucial information about the environment surrounding the burst and the physical processes that occur in the aftermath of such a violent event. By tracking the evolution of the afterglow over time, astronomers can learn more about the density and composition of the surrounding material, as well as the energetics of the explosion itself. The afterglow's fading light curve allows researchers to calculate the total energy released during the gamma-ray burst and compare it to theoretical models. One of the key questions is how the energy from the burst is distributed between the gamma-ray emission and the lower-energy afterglow. This distribution can reveal important details about the mechanisms driving the burst, such as whether the explosion is focused into narrow jets or spreads out more evenly across space. If gamma-ray bursts are indeed jet-like, it implies that we only observe a fraction of the total events, as many bursts would be oriented away from our line of sight and remain undetected. This would suggest that gamma-ray bursts are even more common than current observations indicate, though their true frequency remains a topic of debate. The detection of afterglows in various wavelengths has also been instrumental in pinpointing the locations of gamma-ray bursts. While gamma rays themselves are difficult to trace back to their source due to the lack of directional information, the afterglow can be more precisely localized, allowing astronomers to determine the host galaxy of the burst. This has revealed that gamma-ray bursts are not evenly distributed throughout the universe but are more likely to occur in certain types of galaxies. In particular, long-duration gamma-ray bursts, which are associated with the collapse of massive stars, tend to occur in star-forming galaxies. These galaxies are rich in the young, massive stars that are the progenitors of such bursts. Short-duration gamma-ray bursts, on the other hand, are thought to result from the merger of compact objects, such as neutron stars or black holes, and are found in a wider variety of galaxies, including older, more evolved ones. These differences in the environments of long and short gamma-ray bursts offer important clues about their respective origins and the astrophysical processes that lead to their creation. By studying the host galaxies of gamma-ray bursts, astronomers can piece together a more detailed picture of the life cycles of stars, the conditions that lead to the formation of black holes and neutron stars, and the overall evolution of galaxies. One of the most intriguing aspects of gamma-ray burst research is the connection to gravitational waves. The collision of compact objects, such as neutron stars or black holes, is expected to produce not only a gamma-ray burst but also ripples in the fabric of space-time known as gravitational waves. The detection of both gamma rays and gravitational waves from the same event would provide an unprecedented opportunity to study the physics of extreme gravity and test the predictions of Einstein's theory of general relativity. In 2017, astronomers made the groundbreaking discovery of both gravitational waves and gamma rays from a neutron star merger, marking a new era in multimessenger astronomy. This event, known as GW170817, was a major milestone, as it allowed scientists to study the same astrophysical event through both electromagnetic radiation and gravitational waves, providing a more comprehensive understanding of the underlying processes. This multi-messenger approach has the potential to unlock even more mysteries about the nature of gamma-ray bursts and their progenitors. For example, gravitational waves could reveal information about the masses and spins of the merging objects, while the gamma-ray emission could provide clues about the energy released during the merger and the formation of a black hole or neutron star remnant. By combining these different types of observations, scientists can gain new insights into the fundamental forces of nature, including gravity, electromagnetism, and nuclear physics. Beyond their role as astrophysical laboratories, gamma-ray bursts also offer a unique window into the distant universe. Because they are so bright, gamma-ray bursts can be detected from billions of light-years away, making them some of the most distant objects ever observed. This means that the light we see from these bursts left its source when the universe was much younger, providing a glimpse into the conditions of the early universe. In fact, some of the most distant gamma-ray bursts have been detected from a time when the first stars and galaxies were forming, offering valuable clues about the processes that shaped the early cosmos. By studying the light from these distant bursts, astronomers can learn more about the formation and evolution of the first stars and galaxies, as well as the large-scale structure of the universe. Gamma-ray bursts can also act as cosmic lighthouses, illuminating the intergalactic medium and revealing the presence of gas and dust that would otherwise be difficult to detect. This has led to important discoveries about the distribution of matter in the universe and the processes that drive the evolution of galaxies over cosmic time. Gamma-ray bursts also have implications for cosmology, particularly in the study of the expansion of the universe. Because gamma-ray bursts are so bright, they can be used as standard candles to measure distances across vast cosmic scales. By comparing the observed brightness of a gamma-ray burst to its intrinsic brightness, astronomers can calculate the distance to the burst and use this information to map the expansion of the universe. This technique is similar to the method used with Type I supernovae, which helped to reveal the accelerating expansion of the universe and led to the discovery of dark energy. While gamma-ray bursts are not yet as well understood as supernovae, they hold great potential for probing the large-scale structure of the universe and testing cosmological models. As our understanding of gamma-ray bursts improves, they could become a powerful tool for studying the fundamental properties of the universe, including the nature of dark energy and the shape of space-time itself. In addition to their scientific significance, gamma-ray bursts also raise important philosophical questions about the nature of the universe and our place within it. The sheer power and unpredictability of these events serve as a reminder of the vast forces at work in the cosmos, forces that can shape the destinies of galaxies and potentially even affect the evolution of life on Earth. The possibility that gamma-ray bursts could sterilize entire planets or disrupt the development of intelligent civilizations underscores the fragility of life in the universe and the delicate balance required for life to thrive. At the same time, the study of gamma-ray bursts offers hope that by understanding the forces that shape the universe, we can better protect ourselves from cosmic threats and ensure the long-term survival of life. The detection of gamma-ray bursts and other cosmic phenomena is a testament to the power of human curiosity and ingenuity, as well as our ability to explore and understand the mysteries of the universe. As we continue to study gamma-ray bursts and their implications for the cosmos, we are likely to encounter new challenges and discoveries that push the boundaries of our knowledge. The future of gamma-ray burst research is bright, with new space-based observatories, such as the James Webb Space Telescope, promising to provide even more detailed observations of these enigmatic events. These advances in technology, combined with the growing field of multi-messenger astronomy, will allow us to explore the most extreme environments in the universe and gain new insights into the nature of space, time, and matter. In this rapidly evolving field, researchers are focusing on understanding the connection between gamma-ray bursts and various astrophysical phenomena. One avenue of exploration involves examining the potential link between gamma-ray bursts and the formation of heavy elements in the universe. When massive stars explode as supernovae or merge in catastrophic events, they can produce and disperse heavy elements into the surrounding interstellar medium. This process contributes to the chemical enrichment of galaxies and ultimately affects the formation of new stars and planetary systems. Astrophysicists are particularly interested in the role of gamma-ray bursts in the nucleosynthesis of heavy elements, such as gold and platinum. Some models suggest that the merging of neutron stars, which is often associated with short gamma-ray bursts, can lead to a significant production of these elements through a process known as rapid neutron capture, or the R-process. This hypothesis is bolstered by the observation of gravitational waves and gamma-ray emissions from the same neutron star merger event, which has provided crucial evidence for the synthesis of heavy elements in these cosmic collisions. The study of gamma-ray bursts also intersects with the field of high-energy particle physics. The extreme conditions present during these events can accelerate particles to relativistic speeds, producing high-energy cosmic rays that bombard the Earth. Understanding the mechanisms that generate these energetic particles can shed light on fundamental questions about the origins of cosmic rays and their role in the universe. The interactions between these cosmic rays and the interstellar medium can lead to the production of gamma rays, creating a feedback loop that enhances our understanding of both particle acceleration and gamma-ray emissions. As we delve deeper into the mysteries of gamma-ray bursts, researchers are also exploring the potential implications for astrobiology. The possibility that a nearby gamma-ray burst could pose a threat to life on Earth raises important questions about the resilience of life in the universe. While gamma-ray bursts are incredibly rare events, their destructive power suggests that they could have significant effects on planetary atmospheres, potentially leading to mass extinctions. Understanding the frequency and distribution of gamma-ray bursts, particularly in relation to the locations of potentially habitable planets, could help inform our understanding of the risks faced by life in the cosmos. Another fascinating aspect of gamma-ray bursts is their role in the broader context of cosmic evolution. By studying the distribution of gamma-ray bursts throughout the universe, astronomers can gain insights into the processes that govern star formation and galaxy evolution over cosmic time. The locations of these bursts are often tied to regions of intense star formation, which suggests a relationship between the life cycles of stars and the dynamics of galaxies. By mapping the environments in which gamma-ray bursts occur, scientists can paint a more complete picture of how galaxies evolve and the conditions that give rise to extreme events. Moreover, the study of gamma-ray bursts can also enhance our understanding of the dark ages of the universe, a period shortly after the Big Bang when the first stars and galaxies began to form. During this time, gamma-ray bursts could have played a crucial role in ionizing the surrounding hydrogen gas, thereby shaping the conditions that led to the emergence of the first luminous structures in the universe. Understanding the contributions of gamma-ray bursts to this early phase of cosmic evolution could shed light on the transition from darkness to light, and the subsequent formation of the large-scale structures we observe today. The importance of gamma-ray bursts extends beyond the realm of pure astrophysics. Their study also has implications for the development of observational techniques and technologies. The need for precise measurements and rapid follow-up observations has led to the advancement of instruments and methodologies used in gamma-ray astronomy. The success of space-based observatories, such as the Swift Gamma-Ray Burst mission and the Fermi Gamma-Ray Space Telescope, has paved the way for the next generation of missions designed to investigate high-energy phenomena in the universe. The field of gamma-ray burst research has also benefited from international collaborations and interdisciplinary approaches. The complexity of these events necessitates input from various fields, including theoretical astrophysics, observational astronomy, and computational modeling. By bringing together experts from different backgrounds, researchers can tackle the multifaceted challenges posed by gamma-ray bursts and work towards a more unified understanding of these cosmic phenomena. As our understanding of gamma-ray bursts continues to grow, so too does the potential for new discoveries that could reshape our view of the universe. The mysteries surrounding these extraordinary events serve as a powerful reminder of the vast unknowns that still lie ahead in our exploration of the cosmos. Each new observation brings us closer to unlocking the secrets of gamma-ray bursts, revealing not only their origins and mechanisms, but also their broader implications for the universe as a whole. The future of gamma-ray burst research promises to be exciting and transformative, with the potential for groundbreaking discoveries that deepen our understanding of the universe's most energetic phenomena. As we continue to develop advanced observational techniques and theoretical models, we stand on the brink of a new era in astrophysics, one where the mysteries of gamma-ray bursts may finally be unraveled, providing invaluable insights into the workings of the cosmos and our place within it. Gamma-ray bursts represent one of the most significant and enigmatic phenomena in the universe. Their immense energy, brief duration, and profound implications for our understanding of astrophysics make them a focal point of research and inquiry. As we continue to explore these cosmic explosions, we will undoubtedly uncover new layers of complexity and wonder, enriching our understanding of the universe and the fundamental processes that govern its evolution. The study of gamma-ray bursts not only expands our knowledge of the cosmos but also invites us to reflect on the nature of existence itself, reminding us of the beauty and fragility of life in a universe filled with unimaginable forces and mysteries. Through the ongoing efforts of researchers and astronomers around the world, the quest to unravel the mysteries of gamma-ray bursts will continue, offering new insights and revelations about the cosmos and the forces that shape it. Each breakthrough brings us closer to understanding not only the origins of these high-energy phenomena but also the profound implications they hold for the universe and our place within it. As we forge ahead into the future, the mysteries of gamma-ray bursts will undoubtedly inspire new generations of scientists and enthusiasts, driving the exploration of the cosmos and the search for knowledge in an ever-expanding universe. As we delve deeper into the understanding of gamma-ray bursts, GRBs, it becomes apparent that they are not just isolated events but are intricately linked to the broader tapestry of the universe. One of the exciting aspects of gamma-ray bursts is their potential to reveal information about the early universe. Because these bursts can be observed from vast distances, they serve as cosmic beacons, illuminating the conditions that existed shortly after the Big Bang. By studying the light curves and spectra of distant GRBs, astronomers can glean insights into the properties of the universe during its infancy. The study of GRBs has also provided valuable insights into the evolution of galaxies. The locations of long-duration GRBs, which are associated with the deaths of massive stars, often correlate with regions of active star formation. This relationship suggests that these explosive events play a role in the feedback mechanisms that regulate star formation in galaxies. As massive stars explode, they inject energy and heavy elements into their surroundings, influencing the gas dynamics and chemical composition of their host galaxies. This interplay between star formation and GRBs is a crucial aspect of understanding galaxy evolution and the life cycle of matter in the universe. Another intriguing line of inquiry involves the potential connection between GRBs and dark matter. While the exact nature of dark matter remains one of the most significant unsolved mysteries in astrophysics, some researchers speculate that interactions between GRBs and dark matter could provide valuable clues about its properties. For example, if dark matter particles interact with normal matter in ways that are not yet fully understood, they could influence the environments in which GRBs occur or affect the processes that lead to their formation. Investigating these potential connections may help bridge the gap between the visible and invisible components of the universe, shedding light on the elusive nature of dark matter. The quest to understand GRBs also raises questions about the potential for life elsewhere in the universe. The destructive power of these explosions could pose significant threats to life on nearby planets. For instance, a GRB occurring within a certain distance from Earth could lead to substantial damage to the ozone layer, increasing the levels of harmful radiation that reach the surface. This line of inquiry prompts us to consider how many other planets in the universe might be vulnerable to such events, and what the implications might be for the emergence and sustainability of life beyond our own planet. In recent years, advances in technology and observational techniques have revolutionized the study of gamma-ray bursts. The advent of powerful telescopes and instruments has allowed astronomers to capture data at unprecedented resolutions and sensitivities. For instance, the use of high-energy gamma-ray detectors has enabled the identification of previously unobserved populations of GRBs, expanding our understanding of their distribution and frequency. Furthermore, the integration of multi-wavelength observations, ranging from radio waves to X-rays, has provided a more comprehensive picture of these explosive events and their aftermath. The role of citizen science has also emerged as a significant factor in advancing our understanding of GRBs. Initiatives that engage amateur astronomers and the public in data collection and analysis have proven invaluable. By harnessing the collective efforts of enthusiastic individuals, researchers can analyze vast amounts of observational data and identify GRBs that might otherwise go unnoticed. This collaborative approach not only accelerates the pace of discovery but also fosters a sense of community among scientists and non-scientists alike. Moreover, the search for gravitational waves resulting from GRB-associated events has opened new avenues for research. The detection of gravitational waves from neutron star mergers has provided a unique perspective on the connections between GRBs and these cataclysmic occurrences. As more gravitational wave events are detected, the potential for correlating them with gamma-ray bursts will enhance our understanding of the physics underlying these phenomena, allowing for more nuanced models of their origins and effects. In addition to the scientific implications, the cultural significance of gamma-ray bursts cannot be overlooked. These cosmic phenomena capture the imagination of both scientists and the general public alike. The sheer scale and energy associated with GRBs challenge our understanding of the universe and provoke profound questions about our place within it. This intrigue has permeated popular culture, inspiring works of fiction, documentaries, and public outreach initiatives aimed at engaging audiences with the mysteries of the cosmos. As we reflect on the significance of gamma-ray bursts, we are reminded of the broader themes of exploration and discovery that define humanity's relationship with the universe. The quest to understand GRBs exemplifies the spirit of scientific inquiry, pushing the boundaries of our knowledge and challenging us to confront the unknown. Each discovery brings with it new questions, inviting future generations of researchers to continue the exploration of these cosmic enigmas. The pursuit of knowledge about gamma-ray bursts is not merely an academic exercise. It embodies the desire to understand the fundamental laws of nature and the origins of the universe. As we unlock the mysteries of these extraordinary events, we gain deeper insights into the processes that govern the cosmos, the evolution of galaxies, and the potential for life in the universe. Gamma-ray bursts stand as a testament to the dynamic and complex nature of the universe. Their study not only enriches our understanding of high-energy astrophysics but also sheds light on broader cosmic phenomena, including galaxy evolution, dark matter, and the conditions for life. As researchers continue to explore the intricacies of these explosive events, we can anticipate a future filled with discoveries that will reshape our understanding of the cosmos and inspire generations to come. The mysteries of gamma-ray bursts remind us of the vastness of the universe and the profound questions that still await answers, inviting us to embark on an ever-deepening journey of exploration and wonder. As we continue our exploration of gamma-ray bursts, GRBs, it is crucial to consider the implications of these events for understanding the fabric of spacetime itself. The immense energy released during a gamma-ray burst is not just a spectacular display of astrophysical power. It has the potential to reveal critical insights into the fundamental laws of physics. In particular, the study of GRBs may help illuminate the nature of gravity, the behavior of matter under extreme conditions, and the interplay between quantum mechanics and general relativity. One of the key areas of interest in relation to GRBs is the concept of relativistic jets. These jets, which are narrow streams of material ejected at nearly the speed of light, are produced during the collapse of massive stars or the mergers of compact objects like neutron stars. The dynamics of these jets provide a unique laboratory for testing theories of relativistic physics, particularly as they relate to the emission of gamma rays and the behavior of particles in extreme gravitational fields. Observing how these jets interact with the surrounding environment offers researchers valuable data to refine existing models and potentially formulate new theories of high-energy astrophysics. Furthermore, the study of GRBs may enhance our understanding of cosmic distances and the expansion of the universe. By analyzing the light curves and redshifts of gamma-ray bursts, astronomers can use them as tools for measuring cosmic distances, much like Type Ia supernovae. Since GRBs are detectable across vast distances, they can serve as markers for mapping the distribution of matter in the universe and determining the rate of its expansion. This aspect of GRB research contributes to the broader field of cosmology and helps address some of the fundamental questions about the nature of dark energy and the ultimate fate of the universe. In addition to their implications for astrophysics and cosmology, gamma-ray bursts also present exciting possibilities for interdisciplinary research. The convergence of astrophysics with fields such as materials science, high-energy physics, and even computer science is becoming increasingly evident. As researchers work to understand the physical mechanisms behind GRBs, they often find themselves collaborating with experts from various disciplines to tackle complex problems that require innovative approaches. This interdisciplinary dialogue can lead to new insights and techniques that benefit not only the study of GRBs but also other areas of scientific inquiry. One particularly intriguing aspect of GRBs is their potential connection to exotic astrophysical objects, such as magnetars, neutron stars with extremely strong magnetic fields. Some theories propose that magnetars could play a role in generating gamma-ray bursts, particularly in short-duration events. The interplay between magnetic fields and relativistic jets may provide new avenues for understanding the underlying mechanisms of GRBs. Investigating the relationship between these two phenomena could yield important insights into the life cycles of neutron stars and the extreme conditions that govern their behavior. The rapid advancements in observational technologies have revolutionized the study of gamma-ray bursts in recent years. The deployment of next-generation space telescopes, such as the James Webb Space Telescope, JWST, and future missions designed to probe high-energy astrophysical phenomena, will undoubtedly enhance our capabilities to observe and analyze GRBs. The ability to collect data across a broader spectrum of wavelengths, from infrared to gamma rays, will allow researchers to build more comprehensive models of these cosmic events and their environments. As we move forward, the quest to understand gamma-ray bursts will also benefit from developments in computational astrophysics. The use of advanced simulations and modeling techniques enables researchers to recreate the conditions surrounding GRBs and explore the complex physics that govern their behavior. These simulations can provide valuable insights into the processes that lead to the formation of relativistic jets, the dynamics of shock waves, and the interactions between high-energy particles and their surroundings. By integrating observational data with theoretical models, scientists can refine their understanding of GRBs and enhance our overall comprehension of the universe. In a broader context, the study of gamma-ray bursts serves as a testament to humanity's insatiable curiosity about the cosmos. The quest to unlock the secrets of these powerful events reflects our innate desire to explore the unknown and to comprehend the fundamental principles that govern the universe. This pursuit not only deepens our understanding of astrophysical phenomena but also inspires future generations to engage with science, technology, engineering, and mathematics STEM fields. Moreover, the stories of discovery and innovation that emerge from the study of GRBs have the potential to capture the public's imagination. Public engagement and outreach initiatives that convey the significance of these cosmic events can foster a sense of wonder and curiosity among people of all ages. By making complex scientific concepts accessible and relatable, we can inspire a new generation of explorers, thinkers, and problem solvers. Gamma-ray bursts represent one of the most profound mysteries of the universe, one that intertwines the realms of high-energy astrophysics, cosmology, and fundamental physics. The study of these explosive phenomena holds the key to unlocking some of the most significant questions about the nature of the cosmos, the origins of heavy elements, and the conditions necessary for life. As we continue to investigate the intricacies of gamma-ray bursts, we are likely to uncover new layers of complexity and meaning that deepen our appreciation for the universe's wonders. Through ongoing research, technological advancements, and interdisciplinary collaboration, the mysteries of gamma-ray bursts will continue to inspire and challenge scientists and enthusiasts alike. Each new discovery promises to enhance our understanding of the cosmos and our place within it, reminding us of the beauty and intricacy of the universe we inhabit. As we embark on this journey of exploration and discovery, we are continually reminded that the universe is vast, mysterious, and filled with wonders waiting to be uncovered. Continuing our exploration of gamma-ray bursts, GRBs, it's important to delve into the broader cosmic implications of these events. As we have established, GRBs are among the most energetic phenomena observed in the universe. They provide a unique opportunity to probe the most extreme physical conditions found anywhere in the cosmos. With the vast energies involved, understanding GRBs helps us to better comprehend the fundamental forces of nature, including the interactions between gravity, electromagnetism, and nuclear forces. One of the areas of research that continues to fascinate scientists is the correlation between GRBs and the formation of heavy elements in the universe. The explosions that produce gamma-ray bursts are thought to occur during the collapse of massive stars, specifically during a supernova event. When these stars explode, they generate conditions conducive to nucleosynthesis, the process by which lighter atomic nuclei fuse to form heavier ones. This synthesis of elements is crucial for the cosmic cycle of matter. For instance, elements like gold, platinum, and uranium are believed to be produced in significant quantities during these explosive events. As the ejecta from a gamma-ray burst spreads out across the universe, it enriches the interstellar medium with these heavy elements, which eventually contribute to the formation of new stars, planets, and potentially life. The role of GRBs in the context of cosmic evolution extends beyond nucleosynthesis. The shock waves generated by these explosions can also trigger star formation in surrounding gas clouds. This process of triggered star formation occurs when the energy from a GRB compresses the surrounding material, causing regions of the gas to collapse under their own gravity and form new stars. Thus, GRBs can be viewed as agents of change within the universe, influencing the life cycle of matter and the evolution of galaxies. The spatial distribution of GRBs also provides clues about their origins and the environments in which they occur. Long-duration GRBs, for instance, are predominantly found in star-forming regions of galaxies, while short-duration GRBs appear to be more evenly distributed throughout the universe. This distinction suggests different progenitor systems. Long GRBs are associated with the deaths of massive stars, while short GRBs are linked to the mergers of compact objects, like neutron stars or black holes. Understanding these progenitor systems helps astronomers piece together the history of star formation in various galaxies and how different environments affect the evolution of massive stars. As the study of GRBs has advanced, so too has the understanding of their afterglows. After the initial burst of gamma rays, a GRB can produce an afterglow that is observable across a wide range of wavelengths, from radio to X-rays. This afterglow provides crucial information about the explosion and its environment. By studying the light curves and spectra of these afterglows, researchers can infer details about the composition of the surrounding medium, the kinetic energy of the outflow, and the magnetic fields involved in the process. This multi-wavelength approach not only enhances our understanding of individual GRBs but also allows for comparisons across different events, contributing to a broader understanding of high-energy astrophysical phenomena. The international collaboration of space and ground-based observatories plays a pivotal role in the study of gamma-ray bursts. Facilities like the Fermi Gamma-Ray Space Telescope and the Swift Observatory have revolutionized the field by providing real-time alerts of GRB detections, allowing astronomers worldwide to quickly observe and analyze these events across multiple wavelengths. This coordinated effort is crucial in capturing the transient nature of GRBs and maximizing the amount of data collected. By pooling resources and expertise from various institutions, scientists can share findings and refine models more effectively, leading to faster advancements in the field. As we consider the future of gamma-ray burst research, the potential for discoveries remains vast. The next generation of telescopes and observatories, such as the upcoming Vera-C, Rubin Observatory and the European Space Agency's LISA, Laser Interferometer Space Antenna, will further enhance our capacity to observe these enigmatic phenomena. With improved sensitivity and resolution, these instruments will allow for more detailed investigations of GRBs, potentially revealing new subclasses or unexpected behaviors that challenge existing theories. Moreover, advancements in computational astrophysics will likely play a significant role in our understanding of gamma-ray bursts. High-performance computing allows researchers to simulate complex physical processes associated with GRBs, from the dynamics of supernova explosions to the behavior of relativistic jets. These simulations can help predict the characteristics of GRB afterglows and their interactions with the surrounding environment, guiding observational efforts and refining theoretical models. As we probe the depths of gamma-ray burst research, it's essential to recognize the interplay between scientific discovery and philosophical inquiry. GRBs challenge our understanding of the universe and prompt profound questions about existence, the nature of reality, and humanity's place within the cosmos. The scale and power of these explosions evoke a sense of wonder, highlighting the intricate and often violent processes that shape the universe. They remind us that our knowledge of the cosmos is still in its infancy, and each discovery unravels more mysteries than it solves. In contemplating the significance of gamma-ray bursts, we must also acknowledge their potential for inspiring future generations. The study of these cosmic phenomena not only contributes to our scientific knowledge but also serves as a catalyst for interest in science, technology, engineering, and mathematics (STEM). By engaging the public through outreach programs and educational initiatives, we can foster curiosity and excitement about the universe. Such efforts are crucial in ensuring that future generations continue the pursuit of knowledge and exploration. Furthermore, the challenges faced in understanding gamma-ray bursts can serve as a metaphor for human resilience and adaptability. Just as scientists grapple with the complexities of GRBs, humanity must confront its own challenges, embracing curiosity and a spirit of inquiry in the face of uncertainty. The quest for knowledge is a journey filled with obstacles, but it is also one rich with discovery, growth, and inspiration. As we conclude this exploration of gamma-ray bursts, we find ourselves on the threshold of an ever-expanding frontier of knowledge. The mysteries of the cosmos beckon us to explore further, to ask deeper questions, and to embrace the unknown. The study of GRBs, with all its complexities and implications, is a testament to humanity's enduring quest for understanding, a journey that will continue to unfold in the years to come. In summary, gamma-ray bursts are not merely astronomical phenomena. They are profound events that shape our understanding of the universe. Their role in nucleosynthesis, star formation, and cosmic evolution underscores their significance in the broader cosmic narrative. As we continue to unravel the mysteries surrounding these explosive events, we are likely to uncover new insights that challenge our understanding of fundamental physics and the nature of reality. The excitement and intrigue of gamma-ray bursts will inspire future generations of scientists, thinkers, and dreamers. Through continued research, collaboration, and public engagement, we can explore the cosmos together, deepening our appreciation for the wonders of the universe and our place within it. Each new discovery will contribute to the ever-evolving story of gamma-ray bursts and the intricate tapestry of the cosmos, reminding us of the beauty, complexity, and mysteries that lie beyond our planet. Continuing our examination of gamma-ray bursts, GRBs, it is essential to acknowledge the role that these phenomena play in our broader understanding of astrophysics and cosmology. Their study has opened new avenues for investigating fundamental questions about the universe, including the origins of cosmic rays, the behavior of matter under extreme conditions, and the nature of black holes. GRBs, being some of the most energetic explosions known to occur in the universe, provide unique laboratories for testing the laws of physics in ways that are not possible under terrestrial conditions. One of the intriguing aspects of gamma-ray bursts is their connection to cosmic rays. Cosmic rays are high-energy particles that bombard the Earth from outer space, with a small fraction originating from supernovae and other cosmic events. The immense energies produced during GRBs are thought to accelerate particles to even higher energies than those produced in traditional supernovae. This acceleration occurs in the shock waves generated by the burst and its afterglow, providing a mechanism for the production of ultra-high-energy cosmic rays. Studying these connections between GRBs and cosmic rays could enhance our understanding of the origins of these enigmatic particles and their impact on the universe. In addition to cosmic rays, gamma-ray bursts also provide insights into the behavior of matter in extreme environments, particularly in relation to relativistic jets. The jets produced by GRBs are streams of particles ejected at speeds approaching that of light, and they contain vast amounts of energy and momentum. Understanding the mechanisms behind the formation and dynamics of these jets can shed light on the physics of black holes and neutron stars, as well as the processes that govern the formation of galaxies and large-scale structures in the universe. These insights are vital for developing comprehensive models of how matter behaves under extreme conditions, which can inform our understanding of a range of astrophysical phenomena. Another fascinating aspect of gamma-ray bursts is their relationship to black holes. Many astrophysicists believe that long-duration GRBs are closely linked to the formation of black holes through the collapse of massive stars. When these stars reach the end of their life cycles, they can undergo a supernova explosion, leaving behind a neutron star or collapsing entirely into a black hole. The energy released during these processes can create the conditions necessary for a GRB. Furthermore, the study of GRBs can provide indirect evidence for the existence of black holes and help refine our understanding of their formation and characteristics. As researchers continue to unravel the mysteries of gamma-ray bursts, technological advancements are playing a crucial role in expanding our capabilities for detection and analysis. For instance, the use of gravitational wave astronomy has emerged as a powerful tool in the study of GRBs, particularly in relation to short-duration bursts believed to be caused by neutron star mergers. The detection of gravitational waves from such events, paired with electromagnetic observations of the corresponding GRBs, has provided a wealth of information about the processes occurring during these explosive phenomena. This synergy between gravitational wave detection and electromagnetic observations represents a significant leap forward in our understanding of the universe. The use of advanced computational methods is also vital for simulating the intricate processes associated with gamma-ray bursts. Numerical simulations allow researchers to model the dynamics of GRB jets, the interaction of the burst with the surrounding medium, and the resulting afterglow. These simulations can yield predictions that can be tested against observational data, providing a feedback loop that refines our theoretical understanding and enhances our ability to interpret the complexities of these events. The continuous improvement in computational power and simulation techniques promises to unlock further secrets of gamma-ray bursts and the physical processes underlying them. In parallel with technological advancements, the collaborative nature of modern astrophysics has been crucial for accelerating the pace of discoveries related to gamma-ray bursts. Global networks of observatories and researchers have enabled a rapid response to GRB detections, facilitating multi-wavelength follow-up observations. This collaborative approach enhances the understanding of GRBs, as data from various wavelengths, ranging from radio waves to gamma rays, provides a comprehensive picture of the events. The combined efforts of astronomers and physicists from around the world have created a dynamic research environment where knowledge is shared, hypotheses are tested, and new insights are generated. The study of gamma-ray bursts also raises profound philosophical questions about the nature of the universe and our place within it. The extreme energies involved in GRBs provoke contemplation about the forces that govern cosmic evolution and the interconnectedness of celestial phenomena. As we probe deeper into the mysteries of the universe, we are confronted with fundamental questions about existence, time, and the limits of human understanding. These questions inspire a sense of awe and wonder, driving our quest for knowledge and encouraging us to explore the unknown. The potential implications of gamma-ray bursts extend beyond the realms of astrophysics and cosmology. They can also inform our understanding of fundamental physical principles, including the nature of time and space. GRBs challenge established theories and prompt scientists to refine existing models or develop new frameworks that can better explain the observed phenomena. This ongoing process of inquiry and revision is central to the scientific method and illustrates the dynamic nature of knowledge. In addition to their scientific significance, gamma-ray bursts have captured the public imagination, becoming a symbol of the grandeur and mystery of the universe. The sheer scale and intensity of these events evoke a sense of cosmic drama, reminding us of the vastness and complexity of the cosmos. Public interest in GRBs can be harnessed to promote scientific literacy and inspire future generations to engage with science and exploration. By sharing the wonders of the universe and the insights gained from studying phenomena like GRBs, we can cultivate a culture of curiosity and inquiry that transcends disciplinary boundaries. As we look toward the future, The study of gamma-ray bursts promises to yield new discoveries and deepen our understanding of the universe. Each new observation, whether it be through improved telescopes, advanced simulations, or collaborative efforts among scientists, adds to the tapestry of knowledge surrounding these enigmatic events. The potential for breakthroughs is immense, as the mysteries of GRBs continue to unfold. In conclusion, gamma-ray bursts represent one of the most profound and enigmatic phenomena in astrophysics. Their explosive nature, coupled with the extreme conditions they create, provides unique opportunities for scientific exploration and inquiry. From the synthesis of heavy elements to the investigation of black holes, GRBs are integral to our understanding of the universe and its fundamental processes. As technology advances and collaboration continues to flourish, the potential for new discoveries is boundless. The quest to understand gamma-ray bursts reflects humanity's enduring curiosity about the cosmos and our desire to unravel the mysteries that lie beyond our world. With each revelation, we draw closer to grasping the profound complexities of the universe, illuminating not only the nature of gamma-ray bursts, but also the intricate interplay of forces that govern all cosmic phenomena. As we continue to study these explosive events, we embark on a journey that not only enhances our scientific knowledge but also enriches our collective human experience, fostering a deeper appreciation for the wonders of the universe and our place within it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.